Hello, welcome to Structural Analysis Made Fun and Easy. This is video on flexibility method. Flexibility method again. So basically, I've got to give credit because I'm using an example and I've been learning from Structural and Stress Analysis, 2nd edition by Dr. T.H.G. Megson, Senior Lecturer in Civil Engineering, now retired, University of Leeds. So copyright of the problem is 2005 Elsevier, retrieved. Basically just using under fair use. So the original problem was from the textbook. So it's example 16.6. Determine the support reaction at B in the prop cantilever shown in figure 16.15a. So it's looking at this. It is figure 16.15 prop cantilever of example 16.6. So basically, just to run you through it here, and I've done my own little diagram. Basically, the static indeterminacy of this fixed beam is 1 because you got VA at A, you got vertical A, horizontal A, and a moment at A. That's 3 reactions, and then you got roller vertical at B, so that's another vertical reaction. So that's static indeterminacy is 4 minus 3 equals 1. So that's basically that's what it says. So the middle intermediate span is L, and the end span is cantilevered by L over 2, and the whole beam has got stiffness of EI. As in so I'll just read the text as well. So what they do is A is the diagram. A shows the existing beam with the support. The unit load on the end is W. R1, R2, that's basically VB, VA, and then MA is equals to M2. So as in example 16.5, which is this is an earlier example in the book, the cantilever in figure 16.15a has a degree of statical indeterminacy equal to 1. Again, we shall choose the support reaction at B, R1, as the indeterminacy. The released or primary structure is shown in figure 16.15b, which is this bit. So they remove the support reaction remove the roller support at B. Then you've got A, B, C, and it's just the cantilever with a point load on the end of length L plus L over 2, which is 3L over 2. And then they're measuring X a bit further down from A left to right. So initially we require the displacement VB0 at B due to the applied load W at C. This may readily be found using the unit load method. Thus, from equation 3 of example 15.9, so I'm going to do another video of the unit load method. Another video of the unit load method. Thus, from equation 3 of example 15.9, I'll do a separate video on that. But basically, so what they're saying is, use this equation to find out the deflection at B due to the point load at C, which is basically what you've got. I've drawn it again in my diagram too. Is the beam just deflects like that, like a diving board, and then you've got a deflection at B and deflection at C. The whole deflection in this condition, when the point load is at the end, the curve is like parabolic all the way along. There's no straight sections of it. So so what he does then is, so VB0 equals the sum integration between 0 and L minus W over EI, which is the point load, over EI, times 3L over 2, which is the length, minus X. So it's basically finding the because that's the moment. But I'm going to do is a separate video on that, and that on this one, and after this 3L over 2 minus x times by minus 1 L minus x and then dx. So that gives you, which gives you VBO equals 7WL cubed over 12EI. And so what I did was I done on my own little diagram. So basically, like here, can you see it? Oh yeah. The deflection at B due to this is the release structure. My diagram number 2. Release structure. Remove support at A. Remove the support at B. Sorry, B. And then you apply. You've got the original W load at the end. The deflection at the position B is equal to 7WL cubed over 12EI. So that's the deflection at B. And the deflection at, just out of interest, the deflection at C would be WL cubed over 3EI. But you don't need that at the moment. We just want 7. VBO is 7W cubed over 12EI. So now we've found that, now we need to work out we need to apply a unit load at where the support B was, and that should restore the deflection back to 0. So we need to find out we apply a unit load of 1 and then find out the deflection due to what unit load of 1. So similarly, the displacement, so here's diagram number C. You apply unit load at 1 at where B was, and then you've got A, B, C. Similarly, the displacement at B due to the unit load at B in the direction of R1 is, he's called it A11 equals L cubed over 3EI. Use equation 7 of example 16.5. So basically, I go back to my, I tried to draw a diagram to show you what I know. On his one, he's applying it downwards, but I think it makes it simpler to understand if you apply it upwards, because the load W makes the beam go down at B, and then so when you apply the unit load at B, we need to find the deflection per unit load at B. So the deflection at B, in my diagram number 3, the deflection at B is the same as a point load at the end of the cantilever, so it's unit load times L. Oh yeah, and L isn't the overall length this time though. L is the distance between A and B. So UL, L cubed over 3EI between A and B. So that's my diagram 3. Apply a unit load at B to restore the deflections in diagram 2 to 0. As in 1, because in the structure in 1 we know for sure there was no deflection at B. So the total sum deflection of the primary release structure and the restored structure, that's got to equal 0. So in diagram 4 I just did a little diagram to show you that between, if you put a unit load at B, you get deflection and curved deflection between A and B, and then you will get a straight deflection between B and C, because it's not bending it directly anymore. It's like it's just like a diving board, but that part of it's straight. So between A and B you've got curved deflection, between B and C it's straight deflection form of the cantilever under unit load. So then to finish off this problem, now we found out the displacement with the release structure and the unit and restoring load. So now we can get we can balance the equation. We can balance those two results. VBO is equal to 7WL cubed over 12EI minus A11 times R1 equals 0. So R1 is equal to 7WL cubed over 12EI minus 3 cubed over 3EI times R1 equals 0. So you just move the 7 to this side, or the L cubed to this side, and you will get 7WL cubed 12EI equals L cubed over 3EI R1, and then if you you've got to take away 1/3. So it's like 1L cubed over 3EI minus L cubed over because it'll be 7W times L cubed over you break this equation up. 7W times L cubed over 12EI minus 3L cubed over 3EI equals R1. Sorry, we just take that to the other side, and then you can let me go back to, let me start that again. Hence, since VBI minus A11 R1 equals 0, so then you get VB0 is 7WL cubed over 12EI minus 3 minus L cubed over 3EI R1. So you move that to the other side, and you've got 7WL over 3 divided by 12EI equals L cubed over 3EI over R1. So divide both sides by L cubed, so that removes L cubed, and then times both sides by 3, so you'll get rid of on R1 you've got rid of L cubed. We've got rid of L cubed on both sides, and so if you times this 7WL by 3, you get 3 over 12 equals 1 over 4. So then you've got EI. So if you times both sides by EI and you eliminate EI, that leaves you with 7W over 4 equals R1. So the reaction 1 is 7W over 4. I might do another little. Maybe I should draw that. Maybe I could just draw that out so you can see what I'm doing. But that's basically it. Very simple, and hopefully you found that video useful. Thanks for watching. Please like and subscribe to the channel. Any comments? If you want me to send the diagrams that I drew, then I can send it to you. And then I'll try and do another video, and we'll do another video on example 15.9, which shows how they get VBI. Thanks for watching. Bye.